as we move into further into this lecture, in the previous one, on the previous page of notes, we were dealing with rational exponents, but we also have radical properties as well that we're going to have to deal with, since we have the ability now to rewrite rational exponents as radicals, and we can also rewrite radicals as rational exponents. Now, we've dealt with radical properties before. So if you look back at radical properties, we had these particular ways to take radicals and break them apart when we were either multiplying two terms together or dividing two terms. And so we're looking to get the radical in simplest form, and we need to follow the radical properties that we learned when we were using them for quadratics and for trig. And so we're going to just look at a few examples here, and we're going to focus on A, B, and C first, because those are more basic. So you can see here in part A, the fact that we have two roots that are the same. They can be combined together through multiplication. Remember that the multiplication can go either direction. You can go either way with that property, and that helps us combine them together to get the cube root of 64. And then you could use your calculator just to test to see if 64 is a perfect cube or not, which it is, and that gives us 4. Same thing with part B. These properties right here can go either direction, so you can see part B, the fourth root of 162 and the fourth root of 2, neither one of them are perfect fourths, so we could combine those back together to get the fourth root of 81, which is a perfect fourth, and then that will equal to 3. Now in part C, we have the cube root of 54. So in this case, we're actually going to have to try to break it up, and what we're looking for here is we're not looking for a perfect square anymore to break it apart, but we're looking for a perfect cube. And so the perfect cube embedded in 54 is actually 27, and when we break that apart, the cube root of 27 becomes 3. Be very careful the way you write these, because you don't want to get the 3 and the root mixed up in that particular answer. So that's 3, and then if you want to write it with a little bit more space, you could write it something like that, so that the 3 doesn't look like, we don't want it to look like it's 3 to the third power and then square root of 2. So that would be confusing when we're looking at our final answer. Now, part D is a little different. In part D, we need to spend a little bit of extra time on, and this is a really challenging process here. Part D requires us to go through the rationalizing the denominator process. So rationalizing the denominator was one of the principles that we learned in simplifying radicals. But because this particular radical has a root other than 2, the rationalizing the denominator process is actually going to be a little bit different, and you need to pay real close attention to this. Now, in this particular example, part D, I'm not real crazy about the way it's typed out, so I'm going to show you a little bit of a different method of it. So I'm going to go to a different page here, so I just want you to kind of follow along. Now, let's review quickly rationalizing the denominator. First of all, that's a square root of 2/5. So with perfect squares, we could take our radical properties and we could break this up in the square root of 2 over square root of 5. And then we would want to rationalize the denominator. Now, what we were doing here is we were actually looking to rationalize the denominator by something that would actually create a perfect square here. So we were trying to create a perfect square. And of course, if you take 5 times 5, you get 25, and that gives you the perfect square. And then of course, that's what we were trying to accomplish, because we knew in the long run that that would eliminate the radical from the denominator. And then of course, in order to do this, rationalizing the denominator process, it was very important that we kept it as a form of the number 1. And so when we did that, we have the square root of 10, and of course we can't reduce that anymore, and that gives us a square root of 10 over 5. So we were trying to create a perfect square. Well, as we do this with higher roots, this process actually becomes a little bit more difficult. So if you can see from example D, we have a 5th root. And of course we can break this up, and this is a little different than the way the example shows on the notes. And I kind of like it a little bit better. Now you can see here that we have the 5th root of 3 over the 5th root of 4. Now this is where it gets a little bit confusing. We need to realize what we're trying to do right there is to get a perfect power of 5. So we're trying to get a 5th root that is a perfect root of 5, if you will. So what we really need to do is, what do we need to multiply the 4 by to get a perfect root of 5? Well, this requires us to kind of know our powers of 5. If we don't know our powers of 5, then we're really just guessing here. And since you don't know your powers of 5 yet, we can just use our calculator. So let's take a look. If I just start here with some basic powers of 5, and if I do, and I'll start with 2 because we know 1 to the 5th power, or actually, you know what, I'll start with 1. 1 raised to the 5th power is just going to simply be 1. 2 raised to the 5th power is going to be 32. 3 raised to the 5th power is going to be 243. Now, if we look at those answers, 1 is a perfect 5th, 32 is a perfect power of 5, 243 is a perfect power of 5. So we're looking for a value here. We want a value that can go here that would be a perfect root of 5. And of course we can choose from 1, 32, or 243, or any number bigger than that. But what we have to consider is that that number that we're going to get in there is also a multiple of 4. And if we look back at this, we can see that 32 is a multiple of 4. So if you look at this, if I'd got a 32 there, if I were able to get a 32 there, that would in essence give me the 5th root of 32, which would be 2, and that would clear that 5th root. So what do I have to put right here that's going to give me the 32 right there? And so that is the huge challenge of rationalizing the denominator of a root that's higher than a square root. And so if we just think back to our basic multiples, what we would do here, and I'll go back as if we were working this problem from the beginning, is I would take the 5th root of 8, and I know that the 5th root of 4 times the 5th root of 8, if I multiply those together, I'm going to get the 5th root of 32. And we know that that's eventually going to equal to 2. But if I take the 5th root of 8 and I multiply it by the denominator, I also have to multiply the numerator because it has to be a form of 1. So we now have found the way to rationalize this denominator, and of course this is going to give me the 5th root of 24 on top, so 3 times 8 is 24, and then 24 is not a perfect 5th root, so I simply leave it like that. And of course that is simplified radical form because we no longer have the radical in the denominator. So you can see that rationalizing the denominator with a root higher than 2 is a challenging process that's going to require a lot of practice on your part. So let's go back to the notes and go down to the examples from sample problem 2, and we have 3 parts for you to work on here. So go ahead and pause the video and try each of those samples. Okay. Now, as you're learning these different powers and roots, until you're able to commit some of these to memory through practice, you need to have your calculator handy and just double check all roots and powers and just see if it ends up becoming perfect or not. And you can look at the cube root of 64. If you punch that into your calculator, what you'll realize is that's a perfect cube. It's actually equal to 4. So 4 to the third power is 64, and so the cube and the power would actually cancel each other out. So no need to break that apart, no need to break that into simpler terms. It actually goes directly in. Now, for part B, the fact that we've given it to you as two separate radicals kind of begs for it to be put together. So we're going to actually multiply these together. And so that's going to give me the cubed root of 125. And if you punch the cube root of 125 into your calculator, you'll actually get 5. Okay? And then the last one is a rationalizing the denominator question. So we have to start off by breaking this apart into two separate pieces. So the fourth root of 7 over the fourth root of 8. And of course I'm looking to rationalize this. And I'm not sure what I want to put in there yet, but I know that this bottom one needs to be a perfect fourth root. And of course, if you're not familiar with your fourth roots yet, you can just go test them. So let's test our fourth roots. So let's, 1 to the fourth is obviously going to be 1. 2 to the fourth is going to be 16. 3 to the fourth, it's going to be 81. And of course, we could keep going on. But if I look here, 16, I know that that is a multiple of 8. And the only thing I have to do is multiply that by 2 to get to 16. And of course, if I multiply by the fourth root of 2 on the bottom, I have to do it in the numerator as well. So that's going to give me the fourth root of 14 on the top. And of course, you can check this. The fourth root, so I can say the fourth root of 16, is going to equal to 2. And so now I'm going to have the fourth root of 14 on top, because that doesn't reduce, and 2 on bottom, and that would be my final simplified answer. So that's simplest radical form. Okay? Now, the first couple of times you rationalize the denominator using a root bigger than 2 is very complicated process. It takes a lot of practice to be able to do this, and it's something that you need to become comfortable with. So be sure to get lots of practice rationalizing denominators.